Alright, welcome back. We are talking today about reactions of carboxylic acids. Now, most plants and fruits and vegetables, well, more specifically, most fruits contain a lot of carboxylic acids. Anything that's sour in some way, like vinegar, lemons, yogurt, rhubarb, and more interestingly and more relevant to what we're about to talk about, more unripe fruits contain carboxylic acids. Now, when fruits ripen, some of these acids react with alcohol molecules to produce esters. Now, these esters give many fruits their characteristic aromas and tastes. So, pardon me, we're going to talk about a bunch of these different reactions, and then I'm going to show you what I mean. One take, let's go. All right, ionization in water. Now, most organic acids are weak acids that ionize only a small extent in water. They form hydronium ions. Now, this is year 11 content, where when we look at this, it's the difference between a strong acid and a weak acid. A strong acid is something that readily gives its protons away. A weak acid is like your aunt hoarding things after Christmas, and you're like, please just give things to the Salvation Army. She's like, no, I must have these hydrogens. Fine, you can take that old weird hydrogen that I had like 20 years ago that I received from a distant lover. About 5% of weak acids ionize in water. So it's a reversible process, and it's written with equilibrium arrows. So it's partial ionization because equilibrium favors the reactants. Just how it is. So here's the fun stuff. Reactions of carboxylic acids with alcohols. Now, esters are made by a condensation reaction between a carboxylic acid and an alcohol. Water is produced. I would have hoped that that would have become apparent with, oh, hang on, let me select the highlighter here. The words condensation reaction, and water is produced. This is the sort of thing where I will almost guaranteed put it as a 1-mark question on a SAC, so pay attention. Hang on. Now, this reaction is known as an esterification reaction. Now, if you have a carboxylic acid, remember carboxylic acid is R, carbon double bonded to an oxygen, and then an OH group, and then an alcohol, which is an OH. We covered this last time. This means not laser pointer, pen. Acid. Now, when you combine a carboxylic acid and an alcohol under acidic conditions, it forms an ester. Now, an ester is a functional group that we have not yet covered this year. It is this, which is a C double bonded to an oxygen and then another oxygen down there. And then it forms another, it goes off and creates it has another side chain at the end. And there we go. Here's our promised fabled water molecule. Right now, esters smell. I believe we made esters last year. And if you remember that, you remember we stunk out the lab. I mean, for once, in a good way, not like that time we microwave toothpaste. If someone else has found this YouTube video, that's probably really confusing to them. But esters smell. Now, here's what I want you to do to start. I want you to write the reaction between ethanoic acid and alcohol, right? So just to remind you, now ethanoic acid is C2. Let me just there. Okay. So it's H. C double bonded to an oxygen. Guess what? I'm about to buy a stylus from Officeworks because I already hate this. So there's my ethanoic acid. And my alcohol is, CH3, CH2, OH. Alright. I'm going to give you exactly 5 seconds to scribble that down. And while you're waiting, now I'm going to give you a little bit of time to get that going, but here's the Jeopardy timer. Alright, I hope you came up with this. So this is ethanoic acid and alcohol plus acidic conditions makes ethyl ethanoate, which is CH3 bonded to a carbon, double bonded oxygen gives us CH2, CH3 down, plus CH2, CH3 down there, plus a water. That's what happens in an esterification reaction. If you're ready for another one, write the reaction between propanoic acid and methanol. Alright? Remember, I'm not going to bother to draw it out. I'm just going to remind you that this is C3. And this is just C. Alright. And with that, Jeopardy timer is right back. And with that, I hope you came up with this, which is what propanoic acid plus methanol makes, which is methyl propanoate. Now, as we haven't covered the naming convention for an ester, let's look at it now. Okay? Now, here is what you need to notice. So we've got YL, and we've got anoate, or noate, right? I feel like it's actually, oh wait, sorry, my bad. Now, here's the thing. Okay, so here, if I select my highlighter, you might be able to see that CH3, aka 1 carbon, is that prefix here, the meth. Now, if I change my color to, say, blue, here I've got 3 carbons. Now, 3 carbons gives us a propan. Now, what you need to remember when it comes to naming ester compounds is this. God, I wish I could just type. Okay, so it's I'm going to change the colors a bit, just to, okay, no, that might, okay, so it's, for naming an ester, what you need to know is it's acid, alcohol, I am currently waiting for the caffeine to kick in. I gotta record like 3 more of these videos today. So it's alcohol. Make the color different. Alcohol, YL. So now, whenever you see the alcohol, here it's methanol, so it becomes methyl. If it was propanol, it would become propyl, ethyl, butyl. Basically, anytime that you would name the side chain the same way with that number of carbons on the end of it, it would be ended with YL, and it's ended with YL here. Now I'll change my color back. God, I love drawing on a trackpad. Alright, acid, and then oh wait. So remember, when we name a ester compound, it becomes alcohol, acid, wait. So here it's methyl propanoate. If we go back one slide, becomes ethyl ethanoate. Alright. Now, here is a fascinating thing where how we got aspirin, aka the #1 pain drug in the world. So, we'll say legally obtained pain drug in the world. Pharmaceutical products are actually developed from traditional medicine a lot of the time. So, there was a Greek doctor back in 400 BCE, Hippocrates, the dude who came up with the Hippocratic Oath, recommended the use of an infusion of willow leaves and bark to assist in childbirth. And until 1829, we were just like, okay, sure, whatever, man. But they found salicin, which is a thing the body converts to salicylic acid, which is the thing that relieves pain. And what they did was they actually created aspirin by esterification, which is this little thing down here, acetylsalicylic acid, which is aspirin. And this is a lot easier on the mouth to swallow, which is why we kind of do it. You can actually do this in a lab. The yield is really low. We do it more complex reaction pathway, which we're going to talk about very, very soon, to produce aspirin on an industrial scale. So, now, reactions of carboxylic acids, we're still going. So here we have, if we're trying to make a ester, make an acid from an ester, what we need to do is the reverse of esterification. Now, the reverse of esterification is called hydrolysis. You could possibly imagine the fact that, let me select my pointer again. Okay, so if so for a condensation, oh my god. I hope you're laughing at this. Please tell me that you're laughing at this. Okay, so for condensation reaction, let me try this. Okay, a condensation reaction has water out. But here, what we have is we have water coming in. Now, the water coming in means that this is a hydrolysis reaction, and hydrolysis means that we are breaking it apart essentially through adding water and heat. You can also call it a hydrolytic reaction too. So what I want you to do now is I want you to write the reaction between ethyl propanoate and water. One more time, here's the Jeopardy counter. Do feel free to pause the video if you hadn't worked that one out already. Now, this is ethyl propanoate. So, what you need to remember is ethyl, the acid one is on the alcohol one is on the right, which is this thing here. I'm gonna change it off blue. I don't like blue. Being temperamental here. And the propan, the 3, which is our acid, is over here. Now, when we add water and break it apart, the acid is formed, and so is the alcohol. This is actually how we make soap. It's something called saponification. Now, I think we have actually done saponification before. So, if you have a triglyceride, which is a molecule that we will talk about later this year, and you add strong sodium hydroxide, you can form glycerol and sodium salts of fatty acids. Now, the sodium salt, what it means is it's actually got the C-double-O here. The C-double-O is this. The hydrogen has just been replaced with the sodium. And that is actually what we use for soap. If you can separate the soap and the glycerol, you actually have soap. You can use metal hydroxides. You use metal hydroxide. This is sodium hydroxide. And sodium salts can actually just be made at room temp. Technically speaking, you can get everything from basically Bunnings and Woolworths. I don't think you can get a Bunsen burner from Bunnings, but you know, that's because it's closed now. Alright, last thing. Reactions of carboxylic acids to form amides. Now, primary amides can be prepared by the reaction of a carboxylic acid with ammonia. Now, this is a reaction which they have taken out of the only part of the 2020 course that matters. However, they still want me to teach you this bit now, so we're going to. Now, this is yet another reaction where we're losing water, so it's a condensation reaction. Now, water is produced, the oxygen just bonds directly to the nitrogen, as the reaction would show from there to there, because that's ionic, and the oxygen is ionic, and the nitrogen has spare electrons to donate. Oh, sorry. Oh god, I completely botched that. Sorry, the carbon is ionic, the oxygen is left. Wow, the caffeine still is not kicked in. So instead, my apologies, it's the carbon bonds to the nitrogen, and suddenly we have this, which is called an amide group. Note the naming convention, despite the fact we will never need to know it. It's ethanamide. Basically, it's ethan because it's C2 and no double bond. And then we got the same amide group that goes all the way up here. That's what an amide group looks like. CONH2 or CONH plus water. Here is one last question. You can do secondary amides, but except by using primary amines rather than ammonia. Draw the reaction between ethanoic acid and methylamine. I'm not even going to put the Jeopardy counter on for that one because VCAR don't want me to teach this to you. Oh look, methylamine, CH3 with an NH2 group, ethanoic acid. Oh, look, water comes out, carbon bonds to nitrogen. Ta-da! A secondary amide and water. Alright, with that, reaction pathways is where our next video is going to take us. Please make sure to complete the Heinemann questions before this time next week. And other than that, I will see you soon.